Okay, welcome to the deep dive. Today we're going to be tackling Amazon Web Services, AWS, the big, massive world of cloud computing. And you've given us a really interesting set of materials. It's almost like a structured course on AWS. So this deep dive is really for you. We're going to go through and try to extract what we think is the essential knowledge to give you a really solid grasp of what AWS is all about.
Yeah, you've got a great set of sources here that kind of take you on a journey from like the very basics of IT and how the cloud evolved, all the way down into specific AWS services, how you architect and build solutions using them. What we want to do is we're going to distill all that down into the core concepts, give you those aha moments, help you feel really well informed without getting too lost in the weeds.
Yeah, I think looking at the materials, they flow really logically, starting with kind of foundational stuff, like what is IT infrastructure and where does cloud fit into that picture, and then getting into the core services in AWS, like EC2, for running virtual servers, S3 for storing your data, VPC for setting up your own, private network within the cloud, IAM for managing all that security and access, and then even getting into how you design systems well on AWS and keeping an eye on costs. So, let's jump right in. Let's start with just the basics of IT, right?
One of the most interesting things from the start is how the material starts with traditional IT infrastructure.
Yeah,
the kind that involves physical data centers. And it's important to understand that the cloud isn't like this completely separate entity. It's really an evolution of these established concepts.
Yeah, absolutely. And, back in the day, companies would have their own on-premises data centers. Think of these big rooms filled with servers, physical servers humming away. And your sources touch on the key components of those servers, like the CPU, which is kind of the brain of the server, doing all the processing, and then the RAM, the short-term memory for running applications. And then, of course, you've got storage, like the hard drives or SSDs that hold all the data. And all these machines need network cards to connect to each other and to the outside world.
Right. And that's where virtualization comes in, which is a truly transformative technology. The material really does a good job explaining how virtualization allows you to take a single powerful physical server and divide it into multiple virtual servers, almost as if one physical computer can act as several independent computers at the same time.
Yeah. So instead of needing 5 separate physical servers, you might have one powerful server running 5 virtual machines, right? And each of those virtual machines can even run a different operating system, like Windows or Linux, all on that same hardware underneath. And the source also mentions things like taking snapshots of these virtual machines. It's almost like, like hitting a pause button and saving the entire state of that virtual machine, which is incredibly useful for backups and recovery and things like that.
Exactly. And then there's how those servers communicate. The internet itself, as your sources point out, is really a massive global network made up of many interconnected smaller networks within a single location, like an office building. You'd have what's called a local area network, a LAN, connecting all the devices, computers, servers, printers, and allowing them to talk to each other.
Right. And when we access websites or use online applications, those are often what are called client-server web applications. The main application logic, the data, lives on these servers, often located in those traditional data centers that we talked about. And your computer or your phone acts as the client, sending requests over the internet to the server, which then processes those requests and sends back a response, like the web page that you're trying to view.
Now, let's contrast that with a cloud model. And the material really highlights this key shift in responsibility. So in the on-premises world, you or your organization are responsible for literally everything, from buying the hardware and setting it up all the way through to operating it, keeping it secure, upgrading it, and so on. This is very much what's called a capital expenditure or CapEx model.
Yeah.
You buy the assets up front.
Yeah, you own the physical equipment and you manage it all, but the cloud really fundamentally changes that. All that underlying infrastructure, the servers, the storage, the networking gear, it's all already built and ready for you to use, and you pay for it differently. So it shifts to an operational expenditure model, or OpEx, where you're essentially renting these computing resources and you pay for what you use.
And it's really important to understand the source emphasizes this, that a data center is not the same thing as the cloud. A data center is a physical building that contains servers. And the cloud takes that physical infrastructure and it adds a sophisticated layer of orchestration and automation on top of it. And this automation allows for things like easily creating new services, deploying software updates, monitoring the entire environment, things that would be much more manual and time-consuming in a traditional data center. So think of the cloud as a highly automated, highly scalable version of a data center, or really a network of data centers.
Yeah, it's like a giant automated network of data centers that you can tap into whenever you need computing resources. The material also briefly mentions, different types of cloud deployments, like private clouds, where you basically have on-premises infrastructure, but you manage it more like a cloud. And then, of course, public clouds like AWS, where, resources are shared among many different users. And then hybrid cloud, where you combine elements of both. And it even mentions multi-cloud, where organizations are using services from multiple different public cloud providers. It's a diverse landscape out there.
It is. It really is. And speaking of the landscape, let's zoom out and talk about AWS global infrastructure. It's a really foundational concept. So AWS organizes its infrastructure into these things called regions, which are essentially geographic areas around the world. And within each region, you have multiple availability zones, or AZs.
Right. So think of, a region is like saying the East Coast of the US or Europe. And availability zones are like separate data centers within that specific region. And they're physically isolated from each other, which is really important to minimize the risk of a single failure impacting multiple zones. So if there's like a power outage in one AZ, the others in that same region should ideally continue to operate without any problems.
Exactly. And when you're deploying your applications on AWS, one of the first decisions you make is which region you're going to use. And the material highlights several key factors to consider in choosing a region. There's data compliance, which is, depending on industry regulations and legal requirements, you might need to make sure that your data physically resides in a specific geographic boundary. And there's proximity to your users. You want to, achieve low latency, which means a faster, more responsive user experience for your applications. And of course, you need to make sure that the region that you choose offers the specific AWS services that your application needs. And then finally, pricing can actually vary a little bit between different regions. So that's another thing to keep in mind as you're trying to optimize your costs.
Yeah. The source also mentions AWS local zones, which sound like an extension of this availability zone concept. It's bringing certain AWS services even closer to specific metropolitan areas. I guess the idea there is to provide even lower latency for applications that are super sensitive to those kinds of network delays.
Right. Now let's talk about a crucial aspect of using AWS, which is security, and specifically AWS Identity and Access Management, or IAM. And the material does a really nice job of emphasizing the fundamental purpose of IAM, which is to manage who has access to your AWS resources and what actions they're allowed to perform. It's about establishing identities. It's about authenticating those identities to confirm that they are who they say they are. And then it's about authorizing, once they've been authenticated, what actions they're actually permitted to do. It's really the gatekeeper to your entire AWS environment.
Yeah, that's a great analogy. And IMM has a range of really valuable features. It allows you to grant different individuals or applications shared access to your AWS account without having to share your actual root account credentials, which is a huge security risk. And you can define really granular permissions. So you can say this person is allowed to read data from this database, but they're explicitly not allowed to delete it. And it supports things like multi-factor authentication, or MFA, which is adding an extra layer of security, requiring a second verification factor beyond just a password.
And what's particularly powerful is this concept of identity federation, which allows users from your existing corporate directory, like Active Directory, to actually access AWS resources using those credentials without having to create separate AWS usernames and passwords. IAM also maintains detailed audit logs, which are crucial for tracking who did what and when, both for security monitoring and compliance reasons. It's even certified for PCI compliance, which is crucial for any organization that handles payment card information. And it integrates with virtually all other AWS services. It's a central part of how AWS thinks about security. And the source correctly points out that IAM operates on the principle of eventual consistency, meaning that
that changes may take a short time to propagate across the entire system. And the IAM service itself is free to use, although, of course, you'll pay for the other AWS services that IAM helps you secure.
Finally, there's the ability to obtain temporary access credentials through the AWS Security Token Service, or SES, which is another very useful feature for enhancing security.
Right. So within IAM, you have these core identity types. You have users, which represent, individuals, people, or applications that need to interact with AWS. You have groups, which are collections of users, so it makes it easy to manage permissions for multiple people all at once. And then you have roles, which are like temporary sets of permissions that can be assumed by anyone who needs them, whether it's an application running on an EC2 virtual server or another AWS service that's, that needs to act on your behalf. And all of these identities get their specific permissions by having policies attached to them.
And the material also highlights some critical IAM best practices. The most important one is lock away your root user access keys. The root user is this account that has unrestricted access to everything in your AWS account. So you really don't want to use those credentials for your day-to-day administrative tasks. Create IAM users with only the necessary permissions, and definitely enable multi-factor authentication for your root user and any other IAM users who have elevated privileges. These source even mentions the default password policy for IAM users, which requires a minimum length and a mix of different character types. And it's also worth knowing which tasks still actually require the use of your root user credentials. Things like making changes to your AWS account settings, recovering administrator permissions if they've been lost, or actually closing your AWS account. Those all require root credentials.
So moving on from security for a minute, let's talk about, why are organizations choosing to adopt the AWS cloud in the first place? The sources list a number of really compelling advantages. And I think, a big one we already discussed is the shift from capital expenditure to operational expenditure. Instead of buying all this hardware up front, you're just paying for the resources you use. And then there's the incredible economies of scale that AWS can achieve by operating this massive infrastructure. And those cost savings are often passed on to you, the customer.
And the elasticity of the cloud is a game changer. You no longer need to try to predict exactly how much computing capacity you're going to need months or even years in advance. With AWS, you can scale your resources up or down almost instantaneously in response to the actual demand on your applications. And this leads to a real increase in speed and agility. You can, spit up new environments for development or testing. You can deploy new applications much faster than you could with traditional infrastructure. And you no longer have to worry about the burden of managing and maintaining all these physical data centers. And you also get the ability to deploy your applications globally, reaching users around the world with lower latency by hosting your services closer to them.
And from a market perspective, the material really highlights, using AWS can lead to less staff time being spent on these deployments, faster time to market for new features and products, and increased overall productivity for your development teams. And, the on-demand access to resources, the elimination of infrastructure management worries, not having to constantly plan for future capacity all contribute to that. And of course, the pay-as-you-go pricing and the potential for lower overall costs are major drivers as well.
Now, let's dig into a little bit of networking. AWS Virtual Private Cloud, or VPC. The source describes this as essentially your own private data center that exists within the AWS cloud. And it's isolated to a specific AWS region. So think of it as, you have your own logically isolated network within the larger AWS infrastructure, and you have complete control over how that network is configured, including things like IP address ranges, subnets, routing tables, and so on.
Right. Within a VPC, you can create subnets, which are essentially segments of the IP address range that you've defined for your VPC. And you can launch your various AWS resources into these subnets, things like EC2 instances and databases. And when it comes to connecting your VPC to your existing on-premises network, the material outlines two primary hybrid cloud connectivity options.
Exactly. The first is a virtual private network, or VPN, which establishes an encrypted tunnel over the public internet. VPNs are relatively quick to set up, and they can be very cost-effective, but their reliability and in network latency, how quickly traffic travels through the VPN, can be influenced by the unpredictable nature of internet traffic. The second option is AWS Direct Connect, which creates a dedicated private network connection between your on-premises environment and your AWS VPC. This offers lower latency and higher bandwidth compared to a VPN, but it typically has longer lead times for initial setup, and it can be more expensive. And it's also important to remember that while Direct Connect provides this private connection, the traffic itself is not inherently encrypted. So you might still need to implement encryption at a higher level if your security requirements dictate that.
Okay, so that was a really good grounding in just the sort of basics. Now let's actually start, looking at some of the core AWS services themselves, beginning with, compute, and specifically Elastic Compute Cloud, EC2.
EC2 is really the workhorse of AWS compute. As the material states, it provides resizable compute capacity in the cloud. It's essentially renting virtual servers that you can configure and control. You even get root access to them, giving you a high degree of administrative control. You have the flexibility to start, stop, reboot, and even terminate these instances as your needs change.
Right.
And you have some choices about the underlying hardware that powers those EC2 instances. You can launch instances on shared hosts where your virtual server might be running on the same physical hardware as instances belonging to other AWS customers, or you can opt for dedicated hosts, which are physical servers that are entirely dedicated to running your instances. There's also a default limit on the number of EC2 instances you can run in your account, typically around 20. But AWS can increase this limit if you have a valid business need. And every EC2 instance is launched into a specific subnet within a particular availability zone. And remember, an instance in one AZ can't directly use resources in another AZ as if they were on the same local network.
Right. And the source also makes a very important distinction between EC2 instances that are backed by Elastic Block Storage, or EBS, and those that use instance store volume. So EBS volumes, these provide persistent block level storage, which means that the data on an EBS volume will remain intact even if you stop or terminate your EC2 instance, unless you explicitly delete the volume. So this makes EBS really ideal for things like operating system drives, databases, where data persistence is absolutely crucial. Instance store volumes, on the other hand, provide what's called ephemeral storage, and it offers very fast access to data because it's directly attached to the physical server. But the data on an instance store volume does not persist if the instance is stopped or terminated. So it's suitable more for temporary storage like caches or scratch space.
And connecting to these EC2 instances is also a fundamental task. For Linux-based instances, the standard method is using Secure Shell or SSH, and instead of relying on traditional passwords for authentication, SSH typically uses these things called key pairs, which consist of a private key that you keep securely on your local machine and a public key that AWS stores on your EC2 instance. When you launch an instance, you specify a key pair, and then you use that private key to securely log into the instance. And the material also notes that if you lose your private key, or if you launched an instance without associating a key pair, there are ways to recover access. But it's definitely best practice to manage your key pairs carefully and securely.
And then, for a more integrated console-based approach, the material introduces EC2 Instance Connect. This feature allows you to establish an SSH connection to your Linux instance directly from the AWS Management Console in your web browser. However, it does have certain prerequisites. The instance typically needs to have a public IP address, needs to be running a compatible Amazon machine image or AMI, or have a specific package installed. The IMM user attempting to connect needs to have the necessary permissions, and your security group rules need to allow inbound SSH traffic from specific AWS public IP address ranges.
So let's talk a little bit about security at the individual instance level, and we can use these things called security groups. They're described as virtual firewalls that operate at the network interface level of your EC2 instances. They're really controlling the traffic in and out of your virtual servers.
What's really important to understand about security groups is that you can only define allow rules. There's no such thing as a deny rule. So when traffic attempts to reach your instance, all the applicable allow rules are evaluated. If there isn't an explicit rule that allows the traffic, it's implicitly denied. You can associate up to 5 security groups by default with a single network interface of an EC2 instance, although that limit can be increased. And crucially, security groups are what we call stateful. What this means is if you allow inbound traffic on a specific port, the corresponding outbound response traffic on that same connection is automatically allowed back out, regardless of your outbound security group rules. You can even use security group IDs as the source or destination in your security group rules, allowing you to control traffic between different EC2 instances based on their security group membership rather than just relying on IP addresses.
Right. And then the sources shift to the topic of encryption, which is, absolutely fundamental for protecting the confidentiality of your data. And we have two main types of encryption that we need to think about. We have encryption in transit, which focuses on securing the data as it's being transmitted over a network, and encryption at rest, which focuses on protecting data when it's physically stored somewhere.
Right. The material briefly touches on asymmetric encryption. Yeah. Which uses pairs of keys, a public key for encryption, a private key for decryption, and then symmetric encryption, which uses the same secret key for both encryption and decryption. Asymmetric encryption is often used to securely exchange that symmetric key, because symmetric encryption is generally much more efficient for encrypting large volumes of data.
Right. And to help you manage these cryptographic keys effectively, AWS provides a service called the Key Management Service, or KMS. It's a managed service that allows you to centrally create, manage, and control the encryption keys that are used to protect your data across a wide range of AWS services.
KMS is really critical for meeting various compliance requirements. It adheres to security standards like FIPS 142, is tightly integrated with a vast number of AWS services, making it much easier to actually implement encryption for your data. It's also designed to be highly durable and available. KMS also integrates with AWS CloudTrail, giving you these detailed audit logs of how your keys are actually being used. And while there is a small monthly charge for each custom KMS key that you create, keys that are created and managed by AWS services themselves are provided at no additional cost. The material correctly points out that KMS keys are really the primary resource within KMS, and that AWS generally recommends using symmetric KMS keys whenever possible. And those symmetric keys can be used to directly encrypt and decrypt small amounts of data up to 4 kilobytes in size. But for encrypting larger amounts of data, KMS can generate what are called data keys. You then use that data key to encrypt your actual data, and then you use your KMS key to encrypt that data key itself.
This is known as envelope encryption. And a key security benefit here is that your KMS key itself never actually leaves the secure confines of the KMS service. And KMS never actually stores your unencrypted data encryption keys.
Okay. Next up in our tour of core AWS services, storage with the Simple Storage Service, or S3. And the material starts by really highlighting the key differences between block storage, like EBS, and object storage, which is the underlying model for S3.
That's right. Block storage, it divides data into these fixed size blocks. It stores them along with an index that indicates the location of each block. And the blocks themselves don't actually contain any metadata about the data they hold. So this approach is well suited for workloads like databases that require frequent random read and write access to specific parts of the data. Object storage, on the other hand, treats data as individual objects, and each object consists of the data itself, metadata that describes the data, like its content type or creation date, and a unique identifier. And object storage is ideal for, storing things like images, videos, backups, static website content, data that's, often retrieved in its entirety and may have this associated metadata. And unlike block storage, you can't directly mount object storage as a file system on an operating system.
Right. But object storage offers several key advantages. As your source material points out, it's generally more cost effective for large volumes of unstructured data. It provides excellent scalability and durability, and there are typically no practical limits on the size of individual objects or the amount of metadata that you can associate with them. So it's great for these distributed architectures and for handling massive growth in data. And S3 itself is specifically designed as object storage for the internet. It offers this simple, widely accessible web service interface. You organize your objects into these things called buckets, which are like containers. And the names that you choose for your S3 buckets, they have to be globally unique across all of AWS. And the data within an S3 bucket is then automatically stored across multiple availability zones within a region to provide high availability and data durability.
Let's circle back to IAM for a moment, AWS Identity and Access Management, and specifically focus on IAM access keys. So the material explains that for users who need to interact with AWS programmatically, for example, by using the AWS Fanline interface or CLI or the AWS software development kits or SDKs, they'll need to use what are called access keys. And an IAM access key consists of two parts, an access key ID and a secret access key.
Right, and these access keys allow you to authenticate your programmatic requests to AWS services. And for security reasons, it's important to understand that you can create, modify, view, and rotate these access keys. But the secret access key is only displayed to you when you initially create the access key. Once it's created, you can't retrieve it again, so you need to store it securely. And for using the AWS CLI, you'll typically need to configure your local machine with these access keys. And the source even mentions a standard location where those AWS credentials are often stored, which is in a hidden directory named .aws within your user's home directory.
And then the material revisits IAM again, this time focusing on IAM elements and policies. So IAM policies, we talked about them earlier, are these documents that define permissions. And these policies must be attached to either an IAM identity, like a user, a group, or a role, or in some cases directly to specific AWS resources. And a single IAM identity can have multiple policies attached to it. And the effective permissions are the result of all of those policies combined. They're different types of IAM policies. AWS managed policies are policies that are pre-created and maintained by AWS. They cover common use cases. Customer managed policies are policies that you create and you have full control over. And then there are inline policies, which are policies that are directly embedded within a single IAM user group or role rather than being a separate reusable entity.
Right. And then finally, within this initial overview of key AWS services, the source digs a little deeper into IAM roles. And roles are really a powerful concept because they're essentially IAM identities that can be assumed by anyone who needs them. And this could be an application running on an EC2 instance. It could be another AWS service that that needs to perform actions on your behalf. It could even be another IAM user in your account, or even a different AWS account. When an entity assumes a role, it receives temporary security credentials, which eliminates the need to manage and distribute long-term access keys directly to these entities. You can attach an IAM role to an EC2 instance either at the time you launch the instance or after it's already running. Although an EC2 instance can only have one IAM role associated with it at any given time. And the material correctly points out that IAM roles are universal across all AWS regions, meaning that a role created in one region can be assumed by resources in another region.
Let's shift gears a bit and move on to application integration, and specifically messaging and notification services, specifically Amazon Simple Queue Service or SQS and Amazon Simple Notification Service or SNS. The material starts by contrasting, synchronous communication, where an application sends a request and then waits for a response before it continues, with asynchronous communication, where applications send messages to a queue and they don't expect an immediate reply.
Right. And message queues like SQS play a vital role in building these, what are called loosely coupled applications, especially in these microservices and serverless architectures. They provide a really reliable and scalable way for different components of your application to communicate with each other without being tightly dependent on each other's availability. So when a message is sent to an SQS queue, it's stored there durably until a consumer application retrieves it and processes it. And then typically once it's been processed, the message is deleted from the queue. And this asynchronous model allows you to scale the different parts of your application, the message producers, the queue itself, the message consumers, independently based on their individual workloads and processing speeds.
Amazon SQS is a fully managed message queue service that's offered by AWS. And then we have Amazon SNS, which is described as a fast, flexible, and fully managed publish, subscribe, or PubSub messaging service. So in SNS, you have publishers, which send messages to some specific topics. And then you have subscribers, which receive messages from the topics that they've subscribed to. And SNS supports a wide variety of subscription types, including email, SMS, text messages, Lambda functions, even SQS queues. And SNS is known for its high reliability. It achieves this by storing multiple copies of your messages across multiple availability zones. And it provides security through encryption, both in transit using HTTPS and at rest.
And to round out this initial exploration of key AWS services, this source covers the Amazon Relational Database Service, or RDS. And it starts by differentiating between what are called online transactional processing, or OLTP databases, which are designed for handling real-time transactional workloads with high volumes of short, simple queries. Think of an e-commerce website taking orders, versus online analytical processing, or OLAP databases, which are optimized for complex queries on large data sets for things like business intelligence and analytics, generating reports on sales trends.
Right. So RDS is a fully managed relational database service. It really takes a lot of the operational burden of actually running a database off your hands. It supports a variety of popular relational database engines, including a Microsoft SQL Server, MySQL, MariaDB, PostgreSQL, Oracle, and Amazon's own high-performance MySQL and PostgreSQL compatible database, Aurora. When you launch an RDS database instance, it resides within your AWS Virtual Private Cloud, your VPC. It's important to understand that with RDS, you as the customer, you don't have root level access to the underlying operating system or the database server itself. If you need that level of control and customization, you would typically need to run what we call a self-managed database on an EC2 instance. For security, you can associate security groups with your RDS instances to control network access. And for improved availability and durability, you have the option to deploy your RDS database in what's called a multi-AZ configuration, which automatically provisions a standby instance in a different availability zone.
And for enhanced security, it's generally considered a best practice to launch your RDS database instances in private subnets within your VPC, meaning that they don't have publicly routable IP addresses.
Okay, so that was a fantastic overview of some of the core concepts and this initial set of AWS services. Now your material transitions into some broader architectural considerations with a section on key architecture pillars.
And this part introduces some really fundamental principles that should guide you when you're designing and building applications and systems on the AWS platform. It starts with